continuation of our previous lectures on coagulation mechanism systems. So earlier we've discussed about the plasma-based coagulation mechanism. Today we are going to be looking into the cell-based model of the coagulation mechanism. We have been trying to describe the coagulation mechanism using the two proposed models, the plasma-based and the cell-based model. We've handled the plasma-based model in our part 1. So part 2, we are going to look at the cell-based model or the in vivo or physiologic coagulation mechanism. So the our outline, like we said, is plasma. We've talked about plasma base, which is divided into the extrinsic, intrinsic, the contact, the common pathways. The cell-based model, we have it divided into initiation, propagation, or amplification, and then the clot formation stage. So upon the completion of this course, you are expected, as usual, to be able to have a comprehensive knowledge and also give a critical comprehension of the normal process in hemostasis and thrombosis. And for each of the coagulation complex, the extrinsic tenase, the intrinsic tenase, and the prothrombinase, you should be able to identify the protease, the serine protease, and the cofactor forming the complex, the type of cell that are involved, and the substrates that are being activated. For the plasma-based coagulation model, you should be able to list the factors in their order of reactions, okay? And also, you should be able to describe the cell-based model of coagulation process, and also be able to describe the the role of tissue-bearing cells and platelets in the cell-based model of blood coagulation. So, cell-based model or in vivo physiologic model of coagulation was described by Monroe and Hoffman in 1999. They developed a model of coagulation. They developed a model they used to describe coagulation in vivo, and they were able to demonstrate the mechanisms by which cells influence the coagulation process, because earlier on we've already had the view in the plasma-based coagulation model that hemostasis uh, hemostatic proteins, the proteins of coagulation, play direct and control the process, with the cells serving primarily to provide the phosphatidylserine containing surface on which the procoagulant complexes are assembled. So, but by contrast to the plasma-based model, Monroe and his colleagues proposed a model in which the properties of cell surfaces regulates coagulation. So this model emphasizes the importance of specific cellular receptors for the coagulation proteins. Thus, the cells with similar phosphatidylserine can play very different roles in hemostasis depending on their complement of surface receptors. So the cell-based model, they are they propose that the cell-based model, that in the cell-based model, they propose that coagulation occurs not as a cascade, but in 3 overlapping stages. Stage 1, the initiation, and they propose that this stage occurs on tissue factor-bearing cells. The next stage, the amplification, in which platelets and cofactors are activated to set the stage for large-scale thrombin generation. And the third phase, which is the propagation phase, in which platelets amount of thrombin, which large amounts of thrombin, are generated on platelet surfaces. So the cell-based model, in essence, is a detailed refinement of the traditional plasma-based coagulation model. It consists of 3 cell-bound phases: initiation, amplification, and propagation, We study the phases as though they are discrete, but this is primarily for academic purposes because the three phases are intimately intertwined together. Some researchers even refer to combined amplification and propagation as though they were single phase. That's why you can find some um, being describing it as initiation, amplification, and propagation, and then clot formation. So you can see the diagram shows the phases which are linked together with the larger arrows. They are not separate, they are interlinked. The initiation, the amplification, and the propagation are interlinked together, and all of them are occurring on cell membrane. Okay. So the first phase of the cell-based model of coagulation is the initiation phase, and this occurs in the tissue factor bearing cells. So the initiation phase, as we can see in the diagram, will be thought of as an idling phase with no measurable clinical outcome. Okay, it is no measurable clinical outcome where the tissue factors are constitutive on fibroblasts, smooth muscle cells, or induced on monocytes or endothelial cells. These tissue factors that be these tissue factors upon exposure or decryption cleaves factor 7 to activated factor 7, and both of them forms the tissue factor 7 complex. Then this tissue factor 7 complex cleaves factor 10. The activated factor 10 then cleaves and binds factor 5. The factor 10 factor 5 cleaves prothrombin, forming thrombin. Tissue factor 7 complex also cleaves factor 9. But with no factor 8 around, the factor 9 cannot function. Because remember, we say this process is taking place on the surface on fibroblasts. So around the place where this initiation is taking place, we don't have factor 8. If we look at the normal plasma-based coagulation model of coagulation, we find out that the factor 8 always acts as a cofactor with factor 9. But during this initiation phase, using the cell-based model to describe coagulation, factor 8 is not present at that point of initiation. Hence, the factor 9 that is being activated by the tissue factor 7 complex cannot function. So, and also, initiation proteases are bound and inactivated by tissue factor pathway inhibitor ZPI and antithrombin. Okay, this initiation phase occur away from injury site outside the vessels, often within the lymphatic system. Okay, so this diagram also illustrates the verbal information from the previous slides, where we say that tissue factor is exposed or decrypted. It cleaves and activates factor 7, forming the tissue factor 7 complex. The tissue factor 7 complex then cleaves factor 10, which cleaves and binds factor 5 to form the factor 10 complex. This complex cleaves and activates prothrombin to thrombin. Tissue factor 7 complex also cleaves factor 9. The factor 9 cannot function because of the absence of factor 8. And we say that all the free initiation proteases are also inactivated by tissue factor pathway inhibitor, the ZPI, and the antithrombin. So the process of initiation will be also made possible by some theories that are being described to help describe the process by which the tissue factor 7 complex are being activated and bound together. So there are some tissue factor decryption theories. Okay, when exposed, when we think of only of the tissue factor exposure on injury, we have learned that tissue factor has modest stability for factor 7. Okay, it has modest stability until it is decrypted. So there are 4 proposed mechanisms as shown on this slide to describe this process. The first mechanism we can see, the first mechanism, the negatively charged phosphatidase serine migrates from the inner to outer membrane layer. This first mechanism parallels a plasma membrane function, combining to platelets activation, in which lipid transport enzymes, nicknamed flippase, floppase, and scramblase, rearrange the membrane so that the negatively charged phosphatidase serine moves from the inner to the outer layer to orient plasma factor 7 to join tissue factor and become activated. The second to the fourth mechanism, that's B, C, and D, proposed changes in the tissue factor molecule, including oxidation, dimerization, and fission with phosphatidase serine-rich platelets membrane. So these theories describe the activation of the tissue factor and factor 7 to enable them to form the tissue factor, activated tissue factor 7 complex. So the tissue factor are also blood-borne. We have also tissue factors that are born in the blood. The tissue factor induced on monocytes. Tissue factor can be induced on monocytes and endothelial cells. For example, gram-negative organism lipopolysaccharides. Okay, tissue factor also on polymorphonuclear cells and platelets. Okay, perhaps absorbed from monocytes. Okay, tissue factor circulates on membranous microparticles. Okay, the source may be monocyte and endothelial cells. They may be induced by inflammatory cytokines, and they drive pathological thrombus development and the spread of thrombi. Okay, so the tissue factor, the blood-borne tissue factor, the tissue factor circulates on membranous microparticles induced by inflammatory cytokines, where it drives pathological thrombus formation and the spread of the thrombus. So the second mechanism of the cell-based coagulation model is the amplification phase. The amplification phase begins at the site of the injury. Okay, it starts at the site of injury. Platelets adhere to injury sites through collagen, a von Willebrand factor. Collagen is the most potent platelet activator. Platelets contact thrombin, producing tissue factor bearing cells, and becomes partially activated. Okay, this is called the collagen thrombin stimulated platelets, quotes platelets. Okay, so during amplification, thrombin, in a direct handoff from tissue factor bearing cells, escapes from the antithrombin and bind nearby coat platelets. It triggers release of factor 8 from Willebrand factor and 5 from platelet alpha granules. Cleaves and activates factor 8 to activated factor 8 and factor 5 to activated factor 5. Cleaves factor 8 from its complex with von Willebrand factor. Cleaves and activates factor 11 from plasma and platelet alpha granules. The factor 9 from tissue-bearing cells binds factor 8 on coat platelets. Factor 10 from tissue factor-bearing cells bind factor 5 on coat platelets. Factor 11 bind coat platelet membranes, cleaves and activates factor 9 from plasma or platelets to activated factor 9. So this is a diagram representing the amplification phase of the cell-based model of coagulation. As we said, the thrombin in a direct handoff from the tissue factor-bearing cells, okay, from the tissue factor-bearing cells from the initiation phase, escapes antithrombin. So the antithrombin that meant to neutralize the thrombin at that initiation phase, somehow some thrombin escapes being neutralized by the antithrombin. So when they escape from the tissue-bearing cells and they bind nearby coat platelets, then this triggers the release of factor 8 and von Willebrand factor, okay, complex, and also factor 5 from platelet alpha granules, and cleaves and activates factor 8 and factor 5. It also separates factor 8 from its complex with von Willebrand factor and simultaneously activates factor 11, okay, to form activated factor 11. Factor 9 from the tissue factor-bearing cells binds factor 8 from the coat platelets, and factor 10 from tissue factor-bearing cell bind factor 5 on the surface of the coat platelets. Further, factor 11 and coat platelet membrane, it activates factor 9, okay? So from both plasma, it activates factor 9 to activated factor 9. Okay. The APC control this process, but only in healthy, uninjured tissue. So this is the process of amplification, where the thrombin is able to activate the proteases involved in the coagulation pathway. It's able to activate factor 8, activate factor 5, forming complexes activating factor 9. So the whole process also continues to the next phase. So we have the propagation phase. So in the propagation phase, coat platelet further activated by thrombin, collagen, and von Willebrand factors. Okay. So in this process, the coat platelets are further being activated by thrombin and collagen and von Willebrand factor. The tenase and prothrombinase complexes now assemble on the platelet surfaces. The tissue factor, factor 7, and the factor 10, factor 5 are the extrinsic mechanism. Factor 11 and factor 9, factor 8 are the intrinsic. Yes. The pathways on the platelet surfaces produce high volume thrombin, fibrin polymerization, and stabilization. So in the process of propagation, we have further generation, the platelets are further activated, okay, by thrombin and collagen. So which leads to the further activation of the pathway, and also culminates in activating factor 13 to stabilize and cross-link the fibrin that is also being formed, bringing into account the clot formation. So the propagation phase, as illustrated here, occurs on the coat platelets, which becomes further activated by thrombin, collagen, and von Willebrand factor. The tenase and prothrombinase complex now assemble on the fully activated platelet surface. The pathway on the platelet surface produce high volume thrombin, which cleaves fibrinogen to form fibrin and accomplish fibrin polymerization, cross-linking and stabilizing the fibrin clots. So the process of propagation, okay, which occurs on the cold platelets, ends with the formation of a cross-linked and stabilized fibrin. We can see, as we've seen in the diagram. Okay. So during the process, the cell localization is a central process to the cell-based coagulation model. So tissue factor on cells that support prothrombinase activity, like the fibroblast smooth muscle cells, also on monocyte and endothelial cells, when they are induced. Also, malignant cells that make tissue factor but do not support prothrombinase activity are not as effective. So this phenomenon of cell localization is a central process in the cell-based model of coagulation. Okay, so there are no tissue factor on platelets, so they must adjoin tissue factor bearing cells. No factor 7 or factor 8 receptor site on platelets. Okay, thrombin cleaves protease activated receptor. Then coat activation moves phosphatidylserine to the outer leaflet to support tenase prothrombinase. Coat platelet adhere to injury site via collagen receptor, glycoprotein 6. Glycoprotein 1b59 binds von Willebrand factor, assists coat platelet adherence to injury site. The glycoprotein 2b3a binds fibrinogen and von Willebrand factor. Platelet move provides surface receptor for factor 8, factor 5, 9, 10, and 11. Subsequent non-coat platelets layer damp the reaction. So we have here in vivo contact activation. If you can recall our diagram on the cascade plasma-based model for blood coagulation, we have the extrinsic pathway, the intrinsic pathway, the common pathway, and we have another arm, the contact activation pathway. Okay, so here negative the factor 12 and high molecular weight kininogen, prekallikrein make up this contact activation pathway. So in this pathway, we have factor 12, we have high molecular weight kininogen, and we have prekallikrein. They are the proteins that make up the contact activation system. This contact activation system is an in vitro phenomenon. It occurs in vitro, in which factor 12 is activated in the presence, as you can see in this diagram, in the presence of negatively charged surfaces, such as silica particles, kaolin, silicate, and ellagic acid. But in vivo, this contact pathway can be activated or can be induced by neutrophil extracellular traps. That's the next. They can activate this contact pathway in vivo. Okay, so the contact pathway can be activated in vivo by neutrophil extracellular traps or nests. So stabilized by high molecular weight kininogen, activated factor 12 cleaves and activates factor 11, and coagulation proceeds as we have previously described, activating factor 11 activating factor 9 with its cofactor factor 8 activates factor 10 and down the line. So in this process of factor 12 activating factor 11, prekallikrein becomes cleaved. Prekallikrein becomes cleaved in a serine protease. Kallikrein becomes cleaved in a serine protease. Then kallikrein bypasses factor 11 and cleaves factor 9. Kallikrein also triggers the inflammatory kinase system, creating link with inflammation. Although contact activation is predominantly an in vitro phenomenon, the negatively charged surfaces of prosthesis, such as we have the mechanical heart valves, settings, stents, and the left atrial appendage implants may trigger this process in vivo. Okay. So that is the pathway of the in vivo contact activation. Classically an in vitro process, but can also be activated in vivo by neutrophil extracellular traps and also by negatively charged surface implants in the body. Okay, right. So endothelial cells can become inflammatory. Endothelial cells can become inflammatory. For example, a number of endothelial cell stresses like thrombin, hypoxia, physical injury, DD, AVP, all these can generate stress for the endothelial cells, and when that happens, adhesion molecules, they can generate uh, have some stress. A number of endothelial cell stress can generate adhesion molecules. Okay, they generate these adhesion molecules, have also adhesion molecule binding integrins, the cytokines. Many of them participate in coagulation, thus trying to link inflammation closely to coagulation. Also, we've learned that inflammation are key to thrombus. Hence, in the management of inflammation, antithrombotic agents can be used. So the next slides, this slide tries to show us how the thrombosis and cellular coagulation mechanism have some facts in common. If thrombosis is hemostasis that occurs on endothelial cells, then therapy could target the vulnerable endothelial cells. Aspirin suppression on platelets also slows coagulation. The platelets are not there to participate in coagulation. You can know that the process will be suppressed. Also, certain anti-inflammatory properties can also reduce the recurrence of VTE by up to 30 to 50%. Also, thrombocytopenia slows coagulation. So the process of cellular model for blood coagulation has tremendous advantages. It has so many, it's have enabled us to explain some of the findings we observe in coagulation, which we are not able to previously explain using the plasma-based model. For example, the plasma-based model separates the coagulation cascade into distinct pathways of intrinsic and extrinsic pathway. Now, the question is that if there is a separate tissue factor pathway, okay, why factor 10 activation by factor 8 tissue factor does not compensate for lack of factor 8 or factor 9 in hemophilia. What this place is trying to explain is that if there is if the pathways are separate, why factor 10 activation by factor 7 tissue factor pathway, okay, why does it does not compensate for lack of factor 8 or factor 9? Why does it not compensate for lack of factor 8 or factor 9? This is explained using the tissue factor, the cell-based model, explained in the cell-based model, where we found out that because the factor 7 tissue factor activation of 10 occurs on the wrong cells, for the fibroblast, so, and there are no available factor 8 to contribute, act as cofactor with the factor 9. So the factor 9 cannot function. Also, free factor 10 is inhibited by antithrombin and TFPI. It can only diffuse to a nearby platelet if platelet is nearby. So for the fact that the pathway of the tissue factor, factor 7 activating factor 10 does not compensate for lack of factor 9 or factor 8 is because the activation by tissue factor, factor 7 of factor 10 is occurring on fibroblasts, on the wrong cell and not on platelets. Also, factors 8 or factor 9 deficiency both cause severe bleeding. Why is factor 11 deficiency bleeding variable? This was explained by the fact that the free factor 9 can transfer to platelets as antithrombin has less effect on it. Okay, free factor 9 from the initiation phase can transfer to the platelets because the antithrombin has less effect on the factor 9, and also the factor 9, the free factor 9 on platelet bypasses the need for factor 11. So that explains the reason why the deficiency of factor 9 can be severe, while that of factor 11 may be mild, because the factor 9 can bypass the antithrombin and also bypasses the need for factor 11. Thank you very much for your attention. Thank you.